This is Laplace transforms, and in this video we will be solving initial value problems. Jump discontinuities occur naturally in physical situations that involve switching. So with that, we will need some theory for inverting transforms. So this unit step function was introduced by Oliver Heaviside. And let's take a look at this. The unit step function u of t is defined by u of t equals 0 for t is less than 0 and 1 for t greater than 0. So any Riemann integral, just like the Laplace transform of a function, is unaffected if the integrand's value at a single point is changed by a finite amount. Therefore, we don't need to specify a value for u of t at t equal to 0. We can also use this unit step function to move to a different location. For example, let me just change this color. For example, if we wanted to find u of t minus a, we could have our step function for 0, and this would be u of t minus a equal to 0 for t minus a less than 0, and 1 for t minus a greater than 0. And you know what? I'm going to keep with this same format, putting the 0 first. And this is just equal to zero for t less than a and 1 for a less than t. So now here we have a jump at t equal to a. And here we have a jump at t equal to 0. Also want to show you how else we can modify this step function. We could also have m multiplied by u of t minus a, and here we would have that equal to 0 for t less than a, and m for a less than t. Shifting of the argument of u of t becomes quite simple. We also have something to help us simplify the formulas for piecewise continuous functions. And we have something called the rectangular window function. And this turns the step function on and then turns the step function off. So our rectangular window function, and this is the notation, is defined by what is shown below. And I do want to add that any piecewise continuous function can be expressed in terms of a window and a step function. And we'll get a chance to do that with some examples. Okay, how about translation in T? Happens if we multiply the Laplace transform of a function by e to the as. What happens? And as you can see here, let capital F of s equal the Laplace transform of f. Of course, for s greater than alpha, which is greater than or equal to 0. We have a positive constant a, and we will be using these a lot. So the Laplace transform of f of t minus a multiplied by u of t minus a, all of s, is equal to e to the opposite of as multiplied by the Laplace transform. And we can also represent it using an inverse Laplace transform. So we will be using these a lot, and I went ahead and included these other two Laplace transform formulas. So we will be referring back to these, and you can see that we actually have this last transform, something that's very common, and we see this as a function multiplied by u of t minus a function of t, rather than f of t minus a. So you can see this here, we have a function. This is much more common than this u of t minus a. Whoops. I mean, f of t minus a here. So let's try to put all of this together and look at our first example. We want to sketch the graph of the function and then determine its Laplace transform. So we just talked about this u of t, and that's our unit step function, 0 to 1. And of course, we have t is less than 0 and 0 is less than t. And then we have u of t minus a, and we have 0 when t is less than a, and 1 when a, is less than t. We will first identify our value of a, and a is equal to 1. So our function here is defined as t minus 1 squared multiplied by u of t minus 1, and we see that that is equal to 0 for t is less than 1, and t minus 1 squared for 1 is less than t. And that can be shown right here. See? Graph. So when t is less than 1, of course, we have that the function y is equal to 0, and I have that highlighted here. And then here we have t minus 1 all squared. So that is this part. Okay. So now we do notice that this g of t is of the form f of t minus a multiplied by u of t minus a. So now we will apply our property. So we will use that the Laplace transform of f of t minus a multiplied by u of t minus a of s is equal to e to the negative as power multiplied by that Laplace transform of our function. So let's go ahead and do that. So we now have that the Laplace transform of t minus 1 squared multiplied by u of t minus 1 of s is equal to e to the negative 1s. Of course, I'll just put negative s multiplied by the Laplace transform of t squared. And we have that. That is equal, whoops, put that over there, to e to the negative s, and our Laplace transform of t squared is 2 over s cubed. So we have 2e to the negative s all over s cubed. Okay. There we have it. Let's take a look at our next problem. We can apply the linearity of the Laplace transform and go ahead and write this as the Laplace transform of u of t minus 1 of s minus the Laplace transform of u of t minus 4 of s. And we can remind ourselves of our Laplace transform when f of t is equal to u of t minus a. We have f of s equal to e to the negative as over s. Okay, so let's go ahead and use that here with what we have. So this is equal to e to the negative s over s minus e to the negative 4s all over s. And we have e to the negative s minus e to the negative 4s all over s. Taking a look at this graph, we can see that u of t minus 1, we're going to be subtracting that. Here we have that this function is equal to 0 and 1, and this is when t is less than 1, and this is when 1 is less than t. And here we have this is equal to 0 when t is less than 4 and 1 when 4 is less than t. So if we're just looking on this interval from 0 to 1, you can see that we're going to be 0. Also, if you see that we are going to be between 1 and 4, you can see here we're going to have 1 minus 0, which is equal to 1. So that is why we are have a y value of 1 between those two. And then, I'll go ahead and switch to this color. When we have a t bigger than 4, we do have to take 1 minus 1, which will be these two. And that's going to be equal to 0. And let me just bring this up like that to that point. And this will be the orange. Okay? And that's why the graph looks like that. Okay, let's go on to our next problem. Here, we're going to express this function using window and step functions and compute its Laplace transform. So we are actually going to use the rectangular window function on the intervals 0 to 1, (1 to 2) and 2 to 3. And then for our interval from 3 to infinity, we are going to use our unit step function. Okay, so here we go. We're going to write that g of t is equal to 0, and this is going to be our rectangular window function, and our notation 0, comma 1 of t. We will add 2 times that window function. Let me just get rid of these here and make this a little bit longer. Times the window function from 1 to 2 of t plus 1 times that window function from 2 to 3 of t plus 3 multiplied by u of t minus 3. And what we come up with, of course we will lose this term, is 2 from 1 to 2 of t, 2 times the window function from 1 to 2, plus that window function from 2 to 3 of t, plus 3 u of t minus 3. Now we do have the Laplace transform of the window function that I will go ahead and write at the top, but it is on the table. And we have that when f of t is equal to this window function from a to b of t, of course here 0 is between, a is between 0 and b. We have that our Laplace transform is equal to e to the negative sa power minus e to the negative sb power. And again, a and b are those end of those intervals, those open intervals, divided by s. So let's go ahead and do that right now. So we can say that the Laplace transform of g of s is equal to 2, and let's go ahead and use this Laplace transform over here at the right. So we will have 2 times e to the negative s minus e to the negative 2s all over s, plus, let's take care of this next one, this next window function. We have e to the negative 2s minus e to the negative 3s all over s, and then 3 times u of t minus 3, that Laplace transform. We have that right here. Okay, well, we have that right here, and we will go ahead and use that. Hopefully I didn't move that too much. Okay. So let's go ahead and find that one. And here we have 3e to the negative 3s all over s. So we can actually just place those all over our denominator s. And we have 2e to the negative s minus e to the negative 2s plus 2e to the negative 3s all over s. Okay, let's look at our next example. Express the function using the window and step functions and then compute its Laplace transform. Let's first go ahead and take a look here at our graph. You can see here that we have g of t is equal to 0, and that is when t is less than pi over 2. And as you can see here, we have the sine function, and that's going to be the sine of t when t is greater than pi over 2. So, therefore, g of t is equal to the sine of t multiplied by u of t minus pi over 2. We will go ahead and take the Laplace transform of both sides. So now we will say that the Laplace transform of g of t of s is equal to the Laplace transform of the sine of t multiplied by u of t minus pi over 2 of s. And we have a formula right here with g of t. Right here, our more common Laplace transform. And we will use that. I will go ahead and rewrite that down here. So we note that the Laplace transform of g of t, which is sine of t for us, multiplied by u of t minus a, all of s, is equal to e to the negative as multiplied by the Laplace transform of g of t plus a of s. So we will use that. And we can say that this is equal to e to the negative, because our a is pi over 2, so this is e to the negative pi s over 2, multiplied by the Laplace transform of the sine of t plus pi over 2 of s. And I'll write that here. Okay, so that is equal to e to the pi s over 2 multiplied by the Laplace transform of the cosine of t of s. And then we remind ourselves from our Laplace transform table that when f of t is equal to the cosine of t, whoops, we better put bt, we have that the Laplace transform is equal to s over s squared plus b squared. Let's go ahead and use that. Of course, our b is 1, so we have e to the pi s, whoops, all over 2 multiplied by s over s squared plus 1. And that, we can just put those together in the numerator. Let's just do that right here. So we'll just put that s right here and divide that by s squared plus 1. Okay, let's look at our next problem here. Express the function using window and step functions and then compute its Laplace transform. Let's first write what g of t is here equal. We'll just take each segment. Of course, we can see that g of t is equal to 0 for t less than 1. We can see here that we have g of t equal to t minus 1 when 1 is less than t is less than 2, when we are between 1 and 2. And we have this next segment, which is 3 minus t for 2 is less than t is less than 3. And then we have this last segment is 0, and that is when t is greater than 3. Okay. We're going to use rectangular window function on these 3 intervals here. And then for this last interval, we will use the unit step function. So let's go ahead and we can say that g of t is equal to 0 times that window function from 0 to 1 of t plus t minus 1 multiplied by that window function from 1 to 2. I better move this over here, of t plus 3 minus t multiplied by the window function from 2 to 3 of t. And now let's go ahead and use our unit step function, 0 multiplied by u of t minus 3. Okay, so what we have now we have this term gone and this term gone. So we're working with these 2 middle terms, and by definition of our rectangular window function, we have that this first window function is equal to t minus 1, and then we need to use this definition, which is u of t minus 1 minus u of t minus 2, plus 3 minus t multiplied by u of t minus 2 minus u of t minus 3. So now we have t minus 1 multiplied by u of t minus 1 plus, and we will gather up our t minus 2's here. So we have u of t minus 2 and u of t minus 2. And that will give us 4 minus 2t multiplied by u of t minus 2, plus we have our t minus 3 multiplied by u of t minus 3. And how many of these u of t minus 2's we have right there? We have t minus 1 of them, and then here we're going to have 3 minus t of them. Of course, this is a negative of these t minus 1's. So that's where we come up with 4 minus u of t. So we have negative t minus 1 plus 3 minus t, and that gives us a 2 minus, that gives us a 4 minus 2t. So that's where those are coming from. Okay, so now go ahead and find the Laplace transform. So our Laplace transform of g of t of s is equal to the Laplace transform of t minus 1 multiplied by u of t minus 1, all of s, plus the Laplace transform of 4 minus 2t multiplied by u of t minus 2, all of s, plus the Laplace transform of t minus 3 multiplied by u of t minus 3 of s. So that gives us, e, of course, we're going to use our formula from our table, e to the negative s multiplied by the Laplace transform of t plus 1 minus 1 of s plus e to the negative 2s multiplied by the Laplace transform of 4 minus 2 times t plus 2 of s plus e to the negative 3s multiplied by the Laplace transform of t plus 3 minus 3 of s. So that gives us e to the negative s multiplied by the Laplace transform of just t of s minus 2e to the negative 2s multiplied by the Laplace transform of t of s plus e to the negative 3s multiplied by the Laplace transform of t of s. We can now put all of that together, and we'll remind ourselves that when f of t is equal to t to the nth power, that Laplace transform is n factorial over s to the n plus 1. Of course, our n is just 1, so we have f of t equal to t. So our Laplace transform is just 1 divided by s squared. Okay. So we now have that that's equal to e to the negative s minus 2e to the negative 2s plus e to the negative 3s all over s squared. Okay, let's look at our next example. Let's first remind ourselves about the theorem that gave us the inverse Laplace transform of e to the negative as multiplied by the Laplace transform. So let's remind ourselves that the inverse transform of e to the negative as times that Laplace transform of t is equal to f of t minus a u of t minus a. Okay, so as you can see what we have here that f of s is equal to 1 divided by s squared plus 9. So with that, we also want to remind ourselves that when f of t is equal to the sine of bt, that Laplace transform is b over s squared plus b squared. So remember, when we have the cosine of bt, that's when we have an s in that numerator. So I just want to make sure we are using the table. So now what do we have here? We would need, this is equal to 1 divided by s squared plus 3 squared. So our b is 3. So we would need to have a 3 in the numerator. So our f of t is going to be 1/3 multiplied by the sine of 3t. Okay? So with that, we say that the inverse transform of our f of s of t is equal to 1/3 sine of 3t. And so we have that the Laplace transform of e to the negative 3s divided by s squared plus 9 of t is equal to f of t minus 3, right here, because our a is 3, multiplied by u of t minus 3. And so we'll be using this t minus 3 here. So we will have the sine of 3 times 3, the sine of 3 times t minus 3 all over 3 multiplied by u of t minus 3 which is equal to the sine of 3t minus 9 all over 3 u of t minus 3. Okay, let's take a look at our next problem. Determine the inverse transform of se to the negative 3s divided by s squared plus 4s plus 5. Now this one we're going to do a little bit of algebra. So we see that f of s is equal to s divided by s squared plus 4s plus 5. And that is equal to, and we're going to go ahead and complete the square in the denominator. So that's s plus 2 squared, of course, plus 1. That'll give us our 5. And now let's do a little bit of algebra so that we can use what's in the second column of our table, Laplace transform table. So here we will have s plus 2 squared plus 1 squared again. But I'm going to add 2. And now I'm going to subtract 2. And I'm going to put that 2 on the outside here so we have our form for the table. And so that would be plus 1 squared. So we have that same denominator, okay? So it's negative 2 times that. Okay, so what can we say now? We can say, looking at that form, f of t is equal to the inverse transform of f of s above of t, and that's equal to, so if we take a good look over here, you're going to see that a is equal to negative 2, and b is equal to 1. So we have that this is equal to e to the negative 2t multiplied by the cosine of t. See if I can move this right here. Move this down just a bit. Minus e to the negative 2t multiplied by 2 times the sine of t. So we could go ahead and factor that e to the negative 2t out and have cosine of t minus 2 sine of t. Okay, so now let's go back and look at what we started with. We were actually looking for the inverse of this function, but as you can see, we have e to the 3s multiplied by our f of s that we just computed. So now we have the inverse transform of s e to the negative 3s all over s squared plus 4s plus 5 of t is going to be equal to f of t minus 3 multiplied by u of t minus 3, and that gives us e to the negative 2 multiplied by t minus 3, and here we have our cosine of t minus 3 minus 2 sine of t minus 3 multiplied by u, move this over just a bit, of t minus 3. So I put that in the wrong spot. Okay, let's take a look at the next inverse transform we need to determine. Let's first note that s minus 5 divided by s plus 1 times s plus 2 is equal to negative 6 divided by s plus 1 plus 7 divided by s plus 2. And of course, we used partial fraction decomposition. Okay, so with that, we're actually trying to find the inverse transform of e to the negative 3s multiplied by s minus 5 divided by, and this is what we started with, s plus 1 multiplied by s plus 2, all of t, whoops, is equal to negative 6 multiplied by the inverse transform of e to the negative 3s divided by s plus 1 of t plus 7 multiplied by the inverse transform of e to the negative 3s divided by s plus 2 of t. So now we have that that's equal to negative 6 multiplied by the inverse transform of 1 over s plus 1 plus 7 multiplied by the inverse transform of 1 over s plus 2, all multiplied by t minus 3 u of t minus 3. And now we have that that's equal to negative 6e to the negative t minus 3 plus 7e to the negative 2 multiplied by t minus 3, all multiplied by u of t minus 3. We can now simplify those exponents a little bit, and we have 7e to the 6 minus 2t minus 6e to the 3 minus t u of t minus 3 multiplied by u of t minus 3. Okay. And that concludes this lesson.